and give him plenty of time to give his presentation. I know he has a lot of great visuals, I'm sure, to share with us, and then we'll have plenty of time for discussion at the end. So for those that don't know Ira, he's collaborated and had many discussions with a lot of us here at NASA Ames. So many of you may know him, but for those that don't, Dr. Ira Leifer is a CEO and chief scientist at Bubbleology Research International, and has worked for several decades studying natural and anthropogenic hydrocarbon measurements using in situ and remote sensing techniques. He has many a paper on this subject, and also is the editor of Remote Sensing Journal. So his research focuses primarily on trace gas emissions, measurements with in situ and remote sensing. He was also the chief mission coordinating scientist for the NASA response to the Deepwater Horizon event, and chief scientist of the ESA NASA COMEX campaign. He has developed an in situ mobile truck based system called Sister, and this will be a lot of his presentation that he'll present today for the detection of leaks from oil wells and a lot of other emission sources, which will be discussed. And yeah, so he has a lot of really interesting work, and I'm really excited for him to present all this to us today. And so I'll go ahead and hand the floor over to Ira.
Okay. Thank you for the introduction. I before COVID, I tried to visit Ames, once every few months. Well, maybe a couple of times a year. Haven't done that lately. So this I thought would be a good opportunity to present some recent results and recent capabilities. So we have been working down at the ports of Los Angeles, and we were interested primarily in looking at what the changes were due to COVID and the shutdown. We haven't finished analyzing the data for that. However, we did use the opportunity of one of the refineries and some airborne overflight data to validate our approach. And that's what I'm going to be presenting today. And like to acknowledge some of the key participants in this study, including colleagues from aerospace and UC Irvine. And so first I'm going to introduce Sister, our standard instrumentation suite, truck enabled for response. And some people may remember my crazy science car. We still have it, but we outgrew it. Plus it couldn't do off-road. I then developed a cube or original SIS. We put in a smaller pickup truck. It then outgrew that, and this is the current version, Sister 2, which is a hybrid Ford that has a built-in 7-kilowatt generator to power the equipment. I'd also like to note that SIS is multi-platform. We've installed it on a boat, and my company is developing for sale meteorology trailers, and SIS could easily be put on a trailer as well. So Sister, has a lot of capabilities. We've added more gases. In the upper left is a real-time display. We're going to get into that a little bit more. And we also make measurements of radiation, solar spectra, which I don't have examples of here. On the lower right is a time data for a ceilometer. There's a ceilometer that provides aerosol optical depth profiles. In that case, it was sitting in our driveway when there were wildfire smokes that drifted over the lab. And we even collect Geiger counter data, trying to look at whether there's greater radon emissions in areas where fracking is going on. So this is an example of the real-time display. This is collected about a week ago. You can see the San Joaquin Valley and data showing up of the methane in the real-time display where the airplane, but also values are reported in the left. We saw as high as there's 15 ppm of methane. And so we have real-time readouts also of ozone and other oxidants and so on. You can see the Geiger counter values that need some processing. And we use these real-time data to determine where to go slower, faster. Oops, I didn't want to play that again. Or where to collect samples, canister samples. One of the things we do with Sister is a lot of testing to make sure that things are working. And the way we do that is we climb up the local ridge. Lets us go from my lab at sea level, lower left, to 1,200 meters on the ridge. And this allows us to get out of the dirty marine air and into the cleaner upper air. And so we're looking for notable changes in the structure of the data. So can it actually characterize real variations in the real world? You can see on the lower right. So actually, I better go back. Okay. The wind patterns are typical, but rather unique. So on the plains, they're parallel from the west to the mountains, which are east-west. North is straight ahead. At the ridge, they're coming from the northwest, which is typical. So at the ridge and in the upper atmosphere, they're blowing from inland offshore. But there's also winds blowing up the canyons. So we have this really complex three-dimensionality of the winds, and which on the ridge, air from lower down is blown up into the air that's above. So it gives a really nice testing for our system. So let's go. Temperature normally is a really great way to tell when you get out of the boundary layer, but not when you have inversion layers and it's hotter above than below, which you can see are quite prominent on this day. On the other hand, water vapor, in this case, beautiful designation of the top of the boundary layer and how it rose about 300 meters from when we went up to when we returned down. You can also see in the water vapor at around 1,100 meters, where I kind of have peak one, but sometimes it goes up. So on the ridge, we go up and down and up and down. And so we actually have humid air from below is blowing up. There's repeating patterns in the U, less so in the V, but that is due to those canyon flows that as we climb, we go past. Now to the chemicals. So the methane, well, it agrees very well with the water vapor. Again, from the gray in the background, you can see where dirtier methane-rich air is being blown up in addition to the water vapor. The ethane, which is an ARIS instrument, is capturing repeated patterns on the way up and down related to those canyon flows and does decrease by 1.5 part per billion when we get into the upper air. The propane, this is a brand new analyzer. It's not even listed on ARIS's website for sale. And we're not using it properly yet. We're still trying to figure out how to use it and make sure we get good data. So I'm showing you the warts. We've added a Picaro isotope analyzer, and you can see here that in the upper air, except where it's blowing up from below, it's more biogenic because down on the plains of Goleta, they're both the seeps offshore, onshore, as seeps are natural geological emissions, as well as all the people with their heating and leaks from the pipeline. So, this makes us feel quite confident that the sister would be ready to go out and collect data. And as I've noted, propane. So we climb up to 670 meters on the 154, which has traffic. You can see that in the CO2. You can see it in the CO. At 800 meters, we're on the ridge. There is no traffic. There was some CO and not much CO2. Not sure what's going on there. Somebody's burning something somewhere. N2O shows a change in slope, but otherwise it's a story just diffusing from down below to above with a different vertical mixing rates. So that's good. Um, we screwed up on the ozone data. And so on the 154, it looks good. And you can even see at 600 how ozone's depressed, SO2 and NOx go up, so conservation of oxidants. But then we got onto the ridge road, which is really lousy. And if we're taking our ozone data too fast and the road's too bumpy, the data's not good. The fix is simple. We just need to take the ozone slower. We do have an air suspension that helps us go a little faster. Also showing PM 2.5. And where I pointed out there was that big CO peak. There was also a nice PM peak. We actually record 32 channels of aerosols with our aerosol size spectrum. And we don't have working yet, but we have been trying to get working. It's just on the back burner, a differential mobility analyzer to allow us to look in great detail at the really small particles. Okay, that's our current capabilities. What we're looking at here is Sister 1, which we took down to the port for this study. And you can see the canisters on the roof, which are filled at convenient places. Needless to say, we've been continuously rebuilding this system. So the approach for the study was real-time data winds with Sister, including on a bridge, which allowed us to profile winds up to 60 meters, doing our best to act like an airplane while still staying on the road. MACO, an imaging spectrometer, the thermal infrared, collected at this pretty much simultaneously. I think we were at the plume like 90 seconds apart. Data which was analyzed for column methane. We then invert from the real-time methane data to calculate by a Gaussian plume inversion what the emissions of methane were. And we compared them with MACO, which has you'll just see imaging spectrometry, and we also collect targeted samples. So the ports of LA and Long Beach are the busiest in the Western Hemisphere. At least they were until the supply chain snafu. Nowadays, when we go down there, we don't see anyone doing anything at all, but they were the busiest and they still are very important and busy. And they have quite a bit of industry and refineries in the area around them, wastewater treatment plants, electric generation. Winds blow in from Redondo Beach. They are diverted by Palos Verdes highlands, 450 meters. They reconnect in the western part of the ports in the San Pedro area. From air quality stations are windroses on the left, showing how, except in San Pedro, from my arrow here, except in San Pedro, winds during the day are extremely predictable and coming onshore from the south and across from the Redondo Beach area. So from the point of view of the refineries, you're mostly going to get air that's crossed quite a bit of urban environment before reaching the refinery. Blue shows night, not really relevant for analysis because we were during the day. We collected data 2 times because we weren't ready in June. This is 2020. We weren't ready in June for collecting canisters, but MACO overflew in June. And then in July, we went back and collected canisters, no MACO. And as you can see in both cases, the plume of methane is to the southeast of the refinery, quite repeatable between the 2 surveys. So one of the questions, and this is kind of comes in later, there's a lot of variability in the remote sensing. It's very patchy. And the question is that patchiness due to transport or is it due to emissions? Um, the ACE, which I think is, this is something aerospace does, and I always forget, adaptive coherence something, is very sensitive but not quantitative. And it showed that um, where there weren't plumes in between, there was higher levels of noisy methane. In other words, the plumes are being expanded and contracted or remain unexpanded by turbulence, not by unsteady emissions being the dominant uh, cause of spatial heterogeneity. And just that the levels are below that of the detection for their column. It also showed that there was wind veering going on, that the winds were veering as across the facility. So the refinery is on the left. You can see the tanks. The port is to the right with the water. So here is the column methane. This is quantitative on the left. We identified 3 plumes in it. And Mako derived 2.2 gigagrams per year using sister winds, so about 10% less than if you were using air quality station winds from the nearest air quality station. And the curvature is more clearly shown here. We are on the I-110, so we're actually measuring winds at about 12 meters. The highway is elevated here. So it's pretty ideal for an atmospheric measurement for us in a truck. And you know, the data, one of the things we tried was going into the plume and making a right turn. That was a bad idea. We couldn't analyze that data set. So we didn't do that again. But we also collected some complete transects. We actually had some other goals on that first semi-transect that we were doing. We wanted to get some samples before the airplane arrived. And the 2 canisters that were collected, one of them was collected right in the plume, and then one of them was collected out of the plume in the nearby neighborhood of Wilmington. So 2.2 gigagrams per year. We ran a number of models. I'm not going to get into the details. You can do that in question. Uninformed means we pretend we know nothing from the remote sensing. Informed, we use information from the remote sensing. And we use that, and we can run different assumptions in terms of the total number of plumes that are dominating. So from the, I guess I'm getting into it. From Mako, we know there are 3 plumes, at least 3 easily detectable plumes. Uninformed is where we would have assumed there were 4. That 4th one probably was too small to really discriminate Mako. Point is, our best guess is between 2.5 and 2.7, and Mako was 2.2. So our agreement is within 15%. The uncertainty for Monte Carlo simulations is less than 12%. So this is a very good agreement. We worked at the overall emissions from the plume. So now that we're done being proud of how good we did on the overall plume, when we look at how well we do on the individuals, the answer is terrible. Um, we thought the main plume was plume 1, and Mako said it was plume 2. So what's actually going on is that we're not really putting into our model the veering. And so as a result, we misassign emissions to the wrong plume. So we'd have to improve the model to include the wind veering, either from our own data that we would have collected or from the Mako to do a better job of assigning. But the nice finding is that even though we screwed that up at the sub facility, the facility level emissions were quite robust. And even when we were making poor assumptions, we were agreeing within 25%. Okay. We also collected canisters, and here is shown a comparison of the can methane with the analyzer. Now, since these are manually filled and the times of filling the cans is manually written down, and moreover, they are not filled evenly, I basically am opening a valve but trying to keep it just slowly entering to the canister. There's going to be some uncertainty about exactly what data we're overlapping, plus or minus 20 seconds. And where within that is emphasized. So overall, we're quite happy, we being us and UC Irvine, of the agreement for most of the samples within a couple of percent. So now we're looking at details in the fingerprints of these plumes, and there are some patterns in the alkanes. Note methane is parts per billion. The others are all parts per trillion. So C1 over here is methane. So if the Navy pier, well, it was out in the water and had the cleanest. And so there's no C7, 8, or 9 that were detectable. Detection limits are 3 parts per trillion. Whereas Wilmington, which is the inland, has quite a bit of these larger components. Redondo Beach actually has a surprising amount of these higher components as well, the diesel fraction. We collected it on the beach, on a bluff. There were no visible boats offshore. At the time, and I probably, we thought, and it could be from seeps. It turns out there's an awful lot of abandoned oil wells around Redondo Beach. So that's probably a better explanation of what we're seeing as a clean, we thought it was going to be a clean marine air. The refinery stands well above. And the other difference is the refinery is kind of flat out to pentane, whereas for Wilmington, there's a decrease with alkanes. We also collected 2 samples by some oil wells that are within about 2 miles of the refinery. And they're more similar, I guess, than we were seeing between the refinery and the urban and marine air. But the oil wells also decreased with alkanes, whereas the refinery was pretty flat. Another way of looking at this data, and this includes also a saturation coefficient, which is the pinkness. So the more pink, the more double bonded alkenes and alkynes there are in this demonstration. And then green shows the cyclobenzene, benzene, toluene, and et cetera. So the BTEX. As you can see, Navy, clean air, drops off very fast. Okay, butene quite a bit. If you notice the 66 plume, that's the refinery, flat and very unsaturated. Nice, lots of alkanes. The oil wells, well, they got lots of saturated in them. So the refinery is pulling that out. The oil wells also decrease with alkane. The refinery is flat. So we're looking at basically the refining process. And there's also real enhancement of the diesel fraction, which is over here to the right. H show and G and H show 2 gas stations, one being Chevron and one being Arco. And they have quite different distinct chemical profiles in terms of the saturation. They peak at C5, it is gas. There's not much out in the diesel fraction. Again, not to be surprised, maybe the Arco also did sell some diesels. And very, their BTEX profiles are more like the oil wells. So this is kind of getting into some of the details about how the refining process is changing the character of the oil. Here we show this comparison another way where I've highlighted the diesel fraction. The refinery's got more diesel and it's flat. Okay. So the takeaways from that talk, and then I'm going to go into my more recent material work. We had really good agreement between Mako and Sister, within 20%, even though we made many different assumptions, and the best assumptions were better than 15%. Wind veering is really important, and these are wind veering on scales of 100 meters. So this is not multiple kilometer scale wind veering. It was quite important to understanding and correctly predicting at the sub-facility level. And we showed some fingerprinting. Okay, now we move to work that's going on right now, aside from the port that was published, and please contact me if you can't find the paper. We have a project, a NASA project with Barry to look at emissions from abandoned oil wells. We have a project with the California Energy Commission to fingerprint oil fields, all the oil fields in California, as well as to derive emissions from a number of them. And we also have an NSF project to look at volcanic emissions from Death Valley. I'm not going to really talk about that, but we are going to be doing that within the next month. So I entered into our database of Google Earth all the wells in California. And this is the South San Joaquin Valley, and there are a lot of wells. I'm actually showing 33,000 wells in this Google Earth image. Most of them are abandoned. Some of them are idled, and some of them, of course, are active. We're going to look at some data we've been collecting in the Maricopa area. So this is in the southwest of the San Joaquin Valley. The city of Maricopa is right here on the left, and pretty much the oil fields, almost active oil production, is really just half a mile out of town. And this area here, the Seneca lease, is our focus. And as you can see in this area, there are quite a few active oil wells and a few inactive. And while we came by, active drilling was going on. In fact, that real-time data I showed before was from this active area. We went twice in February, and both times we saw really impressive plumes. That's this were around 2708. The right one shows where canisters were collected. On the 10th, we went to do a fast survey repeat, so we didn't collect any canisters. We've seen methane as high in this data as 55 ppm. But what's really interesting about this data, and up on the left, you can see in the real time that we've integrated the well data when we're out there surveying. So we actually know whether the well in front of us is active, idle, or producing. Is just how much details there are in this plume. Where it goes vertically, that's because we stopped and we're collecting a canister. It doesn't look like a Gaussian plume. It looks kind of square. You can see that in the methane, you can see it in the ethane, you can see it in the carbon dioxide. And then here, we went back in March, still going on, still emitting methane, still seeing this case, we've got up to 26 ppm. And you can look at all the structure, which we highlighted by showing a single transect here in this plume. The point is, it's not coming from just that drilling rig. It's actually coming from many, if not all, of the oil wells in this Seneca lease, this little active area, which we think is really cool. And we'll be we'll be inverting and figuring out how many of them are, which ones it's coming from. But it's kind of suggesting more complexity in the emissions than just coming from where they're drilling. This figure is just demonstrating that our isotope analyzer was also providing some very interesting data from this. Went back. Okay, so that's Project 1, California Energy Commission, looking at emissions from different fields and fingerprinting. The NASA project looking at abandoned California oil wells. We picked this area south of Elk Hills, which is mostly abandoned. And well, actually, no, it's pretty much 100% abandoned. So here we are driving through the oil field. As you can see, there's absolutely no wells anywhere in the area. We're on a dirt road. Occasionally there's a pipe marking something. You know, and there's our real-time data as we're collecting in this abandoned oil field where there's no more methane visible. Sorry, no more wells visible. Now there is a pipeline next to this dirt road, and which were they marked out. So let's look at here's the data from it. So these two main dirt roads have pipelines associated with them. There are a lot of smaller scale dirt roads. The winds are from the northeast. And you can see that there's an enhancement. Okay, so the elephant in the room is that there is a pipeline leak right at the intersection of this dirt room. It's not an elephant. The fact that there are leaks around oil fields is not a big surprise. Although this is a pipeline, there's no wells in this area. And you can see that same plume to the southwest as the winds blow it to another road we transected. But we are clearly seeing an enhancement between the upwind measurements on this actually paved road and the measurements in the dirt area here. So we're talking about 30 part per billion enhancement to upwind of this pipe. So this was a first preliminary look. We wanted to see if we could see something. There is something to see. We're going to go back and do a more comprehensive survey. We did collect a couple of canisters in this area and try to do a better job of understanding what's coming out from these oil wells. But the nice thing is we have several hundred oil wells abandoned in this area, so we can get in one survey a statistical sampling of what the emissions are. We have to pull out what's coming from the pipeline. But this seems a really robust approach to working on the assessing just how much of a legacy does all those abandoned oil wells that the nation's leaving, is how much of a legacy of permanent methane emissions are they likely to do? So you may remember there's way more abandoned oil wells in the San Joaquin Valley right now than there are active producing ones. And so this is a significant problem, and this is the project that we're working on for NASA. And with that, I'm ready for questions.